let me briefly summarize what we did last class. So we look at the interface-enriched generalized finite element method. We saw that this is, in a way, a simpler approach to the modeling of weak discontinuities, right? Remember that a weak discontinuity is a discontinuity in the gradient of the field, right? So the solution has, in a way, a kink. You can represent that as a kink. So what the first thing we did was we look at this problem, which is a bar with a load at the end, and it was fixed on the other end. And we place a discontinuity at the location gamma. And what we wanted to do was to solve this problem with a single finite element. So our partition of unity has basically two shape functions, one that corresponds to the left node that is fixed, and the other shape function is associated to the right node where the load is applied, right? So we have only one standard finite element. And what we decided to do was to enrich that formulation with a term that somehow is able to reproduce that jump in the gradient of the field. So we saw that in the interface-enriched GFEM or IGFEM, that enrichment function is constructed by using the Lagrange shape functions in integration elements. So if this is your original element right here, we basically split that element in two sides, two parts, right? These are called subdomains or integration domains. And then we were using the Lagrange shape functions of integration elements to construct the enrichment function. Yeah. So how is this different from just partitioning that original element into two elements, right? Well, the answer to that is that we do not touch the original partition of unity shape functions. We keep them in place, right? But we add something else. We add something extra. In the end, though, you obtain the same finite element space. So the enriched finite element space resulting from IGFEM and the one obtained by just subdividing that one big element into two elements is basically the same. So in a way, IGFEM is an enriched formulation that is able to recover that standard conforming discretization. Okay. So we went through this example and we saw that how to construct the element stiffness matrices and the force vector, and then we solved it, right? So for this very simple problem, we had a 3x3 degree of freedom system where our generalized degree of freedom alpha and the right node were the only ones free. So here you see we wrote the system of equations, and we also saw that enriched degree of freedom alpha basically represents what you basically need to add to the interpolation of the partition of unity to get to the actual displacement, right? So it has, in a way, a physical interpretation. We also saw that this formulation had a problem. When you are moving that discontinuity towards one of the background nodes of the finite element mesh, then there is an issue with the condition number. So your system becomes more and more ill-conditioned. And in a way, this has to do with the fact that your enrichment functions starts to look more closely to the background partition of unity shape function. So in a way, you're introducing some linear dependency into your problem. We also saw that there was a very simple way to solve this. And what we do is basically we just scale that enrichment function so that when you are moving the discontinuity towards the end nodes, either of them, then that function basically vanishes. It goes to 0. And that scaling factor is proposed here. So it's the square root of 2 times w times 1 minus w, where w is the location of the discontinuity relative to the length of the bar. And this is actually the most optimal scaling factor for this problem, and you can show, and we showed this recently in a paper where you can obtain this analytically from a 1D problem. Now in higher dimensions the formulation stays the same, so we do have the standard component, and then we have an enriched term, and we also looked at the way these enrichment functions are built in higher dimensions. So when you have a triangular element, for example in this case, and that element is cut by a discontinuity, what we do is basically subdivide that background integration element, that background triangular element into integration subdomains, and we use the Lagrange check functions of those integration subdomains to construct these enrichment functions. Here I'm showing two enrichment functions, psi I and j. Okay. Okay. So with all of this is a very quick summary of what IGFEM is. But the only thing that I missed last time is to list the advantages of this approach with regards to the generalized or extended finite element method. This is what I want to do now, just to finish our chapter on IGFEM. So who remembers where are we placing the enrichments in GFEM? Who remembers this? Yeah?
In the elements with the discontinuities.
But where are we adding the enrichments? Yeah, we're doing something to the elements that contain the discontinuities, but the enrichments are placed where?
Elements next to the discontinuity.
No idea? Remember that we talked about clouds, right? So if there was one of the clouds that was basically intersected by one of these discontinuities, what we did was to place an enrichment to the node of that cloud. Remember, the cloud was the set of elements, right, for which the shape function of that particular node was non-zero. So basically, in GFEM or XFEM, we're adding enrichments to the nodes of the background discretization. Okay? In IGFEM, we're adding enrichments to nodes that are created along the discontinuities. Right? So what you see here, for example, is that if I want to construct this psi I function, then I basically create a node right here, and then I associate that node to that enrichment function. So this is the main difference between IGFEM and GFEM. Doves, or degrees of freedom, are added to nodes that are created along the discontinuities. Okay. Again, remember that this idea of a degree of freedom, of a function associated to a unique location in space doesn't make sense. Remember that an enrichment function or a shape function is associated with a set of values for a set of physical locations in your domain where that function is non-zero. Okay, so in a standard finite element, we usually say, well, this shape function corresponds to this node, right? But in fact, that shape function for that particular node is non-zero in the cloud of that function. Okay, the same happens with enrichment functions. What I mean by saying we are adding enriched degrees of freedom to nodes that are created along the discontinuity, I don't mean that the function is only non-zero at that location, right? But it attains its maximum value at that location. Okay, but there is still, that function is going to be non-zero in all that cut element in IGFEM. All right. So one of the main differences with respect to GFEM is that doves are added to nodes along the interfaces. Yeah. Instead of those nodes of the original mesh. Another difference, and well, I guess I can come up with an enrichment function in GFEM for which we have the same property. In IGFEM, the enrichment functions are local to the cut element by construction and are exactly 0 in non-cut elements. Okay? And we talk also about this issue, right? In GFEM or XFEM, depending on the types of enrichment functions that you use, you may have issues in what they are called blending elements. Who remembers what blending elements were? No? No one? Blending elements, tell me?
I thought the transition period
Correct.
between the enrichment and nothing.
Yeah, correct. So blending elements are those elements that are transitioning the standard finite elements from the what we call representative elements, right? So if you have an element that has all its nodes enriched in GFEM, those are called representative elements, right? So next to those elements, right, you may have elements that have few of the nodes enriched. Those are called blending elements. So in GFEM or XFEM, some enrichment functions may have issues in these blending elements, right? So there was this approach proposed by Thomas Fries, where he's actually proposing a modified XFEM formulation to tackle the issue of blending elements. Another important difference is that in our case, the enrichment functions are constructed by using Lagrange functions in integration elements. So in GFEM, we have to subdivide elements for the integration purposes. Remember that we do this subdivision to make sure that integration of those functions is smooth, right? If we are dealing with the functions that are discontinuous, well, you want to integrate those functions in a smooth manner, right? So by creating integration elements, we ensure that we're integrating functions that we know can be integrated with the least number of Gauss points. Okay, so if you have a function with a kink, right, you really want to have an edge of your integration subdomain along that kink, because along that kink, the function or the gradient of the function is not defined, right? Okay. Okay. So again, when we're dealing with discontinuities, we need to create this integration mesh, if you will, right? We need to create these integration subdomains. And in IGFEM, we do not only use those integration elements for integration, we also use them to construct or to help us construct the enrichment functions for the method. Okay? Now, an important one is that if you think about the way we are constructing the enrichment functions in IGFEM, the enrichment functions are exactly 0 at the nodes of the original mesh. Exactly 0. Yeah? And what does this mean? Who can tell me? what are the benefits of having those enrichment functions being exactly 0 at the nodes of the background discretization?
Easier to prescribe boundary conditions.
Yes, that is one of the main advantages, that prescribing essential boundary conditions in the background mesh nodes remains as in standard FEM. What else?
So you preserve partition of unity at the nodes?
You preserve the partition of unity at the nodes. In fact, what you preserve is the Kronecker delta property, okay, of the partition of unity. Yeah. Yeah. Remember that when we're adding an enriched formulation, for the most part, we are not going to preserve the partition of unity property. Okay. This we saw in PFEM, and it's also the case in GFEM. So if you take an element that is enriched and you look at all the functions that are, let's say, active in that element, there is basically no partition of unity. Now, that doesn't mean that you cannot construct a partition of unity, but you have to do something else, okay? But indeed, what you preserve is a Kronecker delta property. And of course, this means that these nodes retain their physical interpretation, as in standard FEM. So this we said already, yeah?
What if an original node is on the discontinuity?
What if an original node is on the discontinuity? Yeah, well, it really depends on the case. You can choose not to enrich there, not to place another node, or you can also do that, right? But this is a particular case that must be handled, right? For example, if you look at a quadrangular element, and if you are cutting, let's say, if your interface is going through two of the corner edges, through the basically opposite nodes, then you have to enrich. Otherwise, you cannot reproduce the field. But if your, let's say, your quadrangular element is being cut only passing through one node, right? Then you can choose not to enrich there, because in a way the background discretization is already able to reproduce this C0 continuity. You see what I mean?
No, not exactly. I thought that was the reason for having enriched FEM. That if the node is on that place, it cannot handle it well, and you don't know where the peak lays.
No. What you want to see is that whenever your discontinuity is going through the element, right, through the element, then that element cannot reproduce the behavior, right? If you have different material properties at either side of the discontinuity, this non-conformity prevents you from capturing the physics, okay? That's where we have to enrich. But let's say now that your discontinuity runs through the edge of an element, right? And then on one side you have some material properties, and on the other side you have other material properties. Then the standard finite element, in fact, this is the way you model this problem with the standard FEM. The standard FEM can already reproduce the right physics because the entire approximation of the standard FEM is C0 continuous. So along that edge, you are able to reproduce the behavior. Yeah? So then the question is, but what happens if your interface goes through only one node? of your discretization, right? So in some cases you can choose not to enrich there because you are relying that the standard finite element node is able to reproduce the behavior, right? But in other cases you have to, right? If you have a case, for example, that is a quadrangular element, and then you are running through the opposite corner nodes, then you have to enrich there. Otherwise, there is no way you can reproduce internally that behavior. You see what I mean now?
Yeah.
Yeah. Yeah. But this is a very interesting question, and yeah, it's one that it made us think a lot about how to handle this case. Yeah. So this is something that we already said. Yeah, we already talked about this. And finally, we also discussed the issue with condition, the condition number of a stiffness matrix. And this is another difference with respect to GFEM, the issue of conditioning. And I'm going to talk a little bit about this. Okay. So this is an important difference. So right now in the generalized finite element community, there is this main drive to search for stable generalized finite element methods. These are called SGFEM. And the idea is that you basically have to choose enrichment functions that remain stable with the method, so that your condition number doesn't blow up when your discontinuities are, for example, approaching nodes of the original mesh. So there is ongoing research in this area, right? What we showed is that with IGFEM, if you provide a scaling of enrichment functions, the method remains stable. And we also showed that even if you don't do anything, if you don't scale those enrichment functions, in which case your stiffness matrix is ill-conditioned, you can really apply a simple preconditioner to the method, some Jacobi-like preconditioner, and then you recover stability. So this is really nice. So this is basically a summary of the advantages of IGFEM over GFEM or XFEM. So with this, we basically finish IGFEM. Do you have any questions up to this point? Yeah?
What about disadvantages?
Well, the disadvantage, let's see. In terms of disadvantages, of course, IGFEM can only be used to model weak discontinuities, right? GFEM, in that sense, is a more general framework. You can pretty much add anything you want to the formulation. And if you have, let's say, a problem with a steep gradient, then if you add an exponential function, the GFEM framework allows you to do this sort of thing. And IGFEM is in many ways a simpler formulation, but it only works for weak discontinuities, right? So it is that is the niche of application. it does not include any singular enrichments, IGFEM. So there are problems for which, for example, you have a singularity that is introduced because, for example, your weak discontinuities meet in a triple junction, for example. So this formulation does not include anything to be able to address those singularities, right? So those are, in a way, our problems in category B, but we are not adding enrichments to improve the formulation, right? Other disadvantages I can think of, well, it's not a disadvantage of IGFEM with respect to XFEM or GFEM per se, but what I would say is that the main disadvantage of all these enriched formulations is that you need to really have a robust geometric engine, you know, dealing with all these cuts and intersect those elements and figure out which elements are cut or not. This requires a nice implementation of a geometric engine to do computational geometry, and this is very tough, and to get it right takes a lot of time. So this is, I would say, the main disadvantage of any enriched formulations for which the discontinuities are resolved implicitly by the formulation. Okay? Yeah, but I think that's it. Any other questions? Okay. All right, so we finished with IGFEM here, and in the next lecture what we're going to do is to look at GFEM for fracture mechanics. Okay?